Okay, welcome everybody. So, I've noticed that all the YouTubers seem to have a really cool intro sequence. So, on a low budget that I have, I've decided to enlist the help of my cat. So, I've been training her for a while, and here we go. Alright, Misha, you're gonna do a song and dance routine for me, okay? Ready? Go. Okay, you can go now. Normally she does a song and dance routine. I'm not sure what's going on. Alright, looks like we're done. Alright, so maybe it needs some work. Alright, but you're here to see a flight, so let's get going. Today's flight is going to be a launch and soar flight. Now, more aptly called a launch and glide flight. So, here we go. Now, there's a peak rating of the motor and there's a continuous rating of the motor. And we want to keep it in the continuous range. Now, the continuous range is actually around 85 amps, but that's not going to give us the climb we want. So we are going to set it at about 120 amps, and we're going to watch the temps. So our motor temp right now is 116. We can go up to 257. We're going to watch the temp also of the motor controller. We can go up to 212 on that. Right now it's 125. We're about 250 feet per minute climb. We want to kind of keep it there. We're at 2100 RPM. Motor temp 163. ESC temp 142. Climbing at 37 miles per hour. We're at about 1,000 feet above the ground. Make a gentle turn. Battery temps are 29 Celsius. 70 Celsius is the alarm temp. So we're doing pretty good. The battery is actually over-designed as far as the size and the current draw. It can do much more than this application. Motor temp at 179. We're at about 4,000 feet now. It's about where Tehachapi is. Outside air temperature 71 degrees. Actually, it was very cold this morning, but it turned out pretty nice. We're at 182 on the temp on the motor, 146 on the controller. Controller last time was 140 the whole time, and we're pushing it, so it's doing really well. Nice view. There's Tehachapi straight ahead of us over there, Tehachapi Mountains. Edwards Air Force Base is right over there. It's where I worked for NASA, and the Air Force actually, for a number of years. Motor temp, 173, it's actually going down. Controller temp's actually going down as well. We got 39% left on the battery. (52C) on the MOS temp, 44C on the battery cell temp. And we are at 5,000 feet now. Density altitude today is 6589. Okay, at 25%, we're gonna call it good and start gliding. Controller temp's gone down. Motor temp has gone down to 175. 70 degrees outside up here at 5,000 feet, 5,200 feet now. Okay, 25%. We're gonna go back on the throttle and fold the prop. Okay, and let's glide. Now this is the fun part. This is my favorite part. I love going up here and shutting off the motor. We want to keep our airspeed up, of course. We're sinking about 500 feet a minute. That's actually quite a bit. Maintaining 37 miles per hour. This wing is a 13 square meter wing, so it's not a lot of surface area. North wing that we have this propulsion system on, they use a 20 square meter wing, and of course that's really big, and Basically, you float around. It takes very little power to stay aloft with a wing like that. And so they have longer flight times, and they sink. The sink is a lot better on that. But downsides to a bigger wing, of course, is a little heavier on the handling. Doesn't handle winds as well. If it's a little windy and gusty, it doesn't quite handle it as well. See if we can do a stall here. Test out the stall characteristics. And forward, and there's the stall. Not bad. Not bad at all. Non-event. And the airspeed on the bigger wings is a little slower. It's more down in the 30s, whereas this is about 40. So. So no thermals, of course. This is early morning here in the desert. It does get thermally in the afternoon, but it does get windy as well. So kind of a not quite as flyable as the early mornings for a light aircraft like this. Alright, coming in for a landing here. Get our airspeed up a little bit so we can get some good floating there in the landing stage. So here we go. And look long, and look long, and here we go. Not too bad. A little bouncy. Now we had 25% left, so we only used 75% of the battery, but we wanted extra just in case. You never know what's going to happen. So just to be safe. Okay, and here we are. We'll look at the data probably later tomorrow. Alright, welcome everybody. We have the data from the flight number 4. And we're going to go over it just quickly. I know the video is kind of long already, so I don't want to keep everybody longer than you have to be. So first of all, just a quick review. On takeoff, we're still hitting about 21 kilowatts, which is what we saw last time. Now, we established a climb of about 250 feet per minute
as you can see over here in climb rate. Um, that's average. We kind of went up and down. I'm not a professional test pilot, but average was 250 feet per minute. At that climb rate, we were seeing about 12 kilowatts of motor power to do that. Now, this is a very, very conservative climb rate. This is our first test on this aircraft with this system, so we wanted to have the first climb test be very conservative. Um, Based on what we found, as you can see, the ESC temp is here. Only got up to about 65 in the middle of our climb, and 100 is the maximum allowable. So we had a lot of margin on the ESC. The motor temp got up to 182 Fahrenheit. Sorry, this is Celsius right here. So I got up to 182 Fahrenheit. The max is 256 Fahrenheit, so there's quite a bit of margin there as well. So the motor and the controller did really well at 250 feet per minute over an extended period of time. Um, the RPM, of course, that we saw at that climb rate was about 2200. Now, one of the things that I mentioned, um, and before I get into that, we climbed to an altitude of about 5,500 feet, which was about 2,500 feet above the ground. So our total climb was 2,500 feet. Climb airspeed, we started out about 37 miles per hour. We gained speed as we made it to the mid climb. And then when we turned off the motor and glided, we came down to about 36 miles per hour. Now, the most important part of this flight was a comment that was made during the flight portion, and that was about the sink rate. Now, the sink rate that we saw during the flight was about 500 feet per minute. And those who know soaring and know gliding know that that's a really high number. Now, I contacted Ben Ashman at Flylight about the wing and asked him about that sink rate. And he said that you can reduce your airspeed by pushing out the bar and reduce that sink rate down to about 216 feet per minute, which is really good. And I wanted to just quickly show you some of the other wings that are normally used for soaring. So this is the Atom wing, which is the one I have right now. You can see that its speed range is from 56 to 21. So 21 is its stall speed. Now, if you had to be pushing the bar out the entire time, if you want to reduce the sink rate down to 216, you'd be getting close to the stall speed. And flying with the bar pushed out the whole time you're soaring may be difficult. It may not be the optimal solution for soaring flight. One of the ways to mitigate that is to change the hang point, which can easily be done. Some more advanced solutions might be electric trim, so that you could trim it electrically, the hang point. from cruise to soaring, and so on. So that's also an option. Now, other wings that are used, Aeros also has a 16-meter wing, which is similar in construction to the Atom wing, but it's 16 meters, so it would definitely give you um, better gliding or soaring characteristics. Um, its minimum airspeed is the same as the Atom wing, the same as a 13 square meter wing. Top speed is less. Um, but with the extra surface area, you definitely get better sink rates. For the US market, North Wing that we have our electric propulsion systems on has what they call the Discovery 207. It's a 207 square foot wing, a 35-foot span, which is actually really long, um, but a 220 foot per minute sink rate, which is really good. Now that sink rate is at 25 miles per hour, which is low. Its stall is 17, so it's not far from stall, and it may be about what you'd see if you were to press the bar out on the Atom wing to try and get to that 216 feet per minute. Um, so take that for what it's worth. You may, now this 220 feet per minute, that might be at the bar at trim, bar neutral, which would make it much easier to fly in that condition. Whereas on the Atom, the way it currently sits at the hang point that I have, um, you would have to constantly press the bar out to get to that low sink rate. Now, the final wing I wanted to show you is the ATOS wing, and this is made in, I believe, Germany. This is probably the ultimate efficient wing for trikes. Typically used for hang gliding, but they do have a version that is put on trikes. The Ego trike, it uses the ATOS wing, and it has a sink rate of 138 feet per minute, or a 19-to-1 glide ratio, which is absolutely amazing for a hang glider style wing to achieve that. That's sailplane like numbers. Um, so that's pretty amazing. So those are the considerations. Now, what this does is it begs a further test. It begs another test to um, test the bar out condition to try and get that sink rate down to around two and in the 200s, and see what the airspeed is, um, and see how close it is to stall speed, and see how that changes our flight endurance and our gliding endurance, um, and see what benefit that gives us. Now, the other thing that I wanted to just briefly mention is that the other way to increase flight time, in addition to reducing sink rate of the wing, is to improve the propulsive efficiency. Now, I currently use a 1.3 meter um, propeller from Helix. Very nice propeller. Um, the 1.3 meter is actually the suggested diameter from Flylight. Um, However, they said that Ben also mentioned that a 1.4 meter propeller could be used. Now, in when you talk about propellers, a larger diameter propeller turning slowly is more efficient than a smaller diameter propeller turning quickly. So what we can do to improve our propulsive efficiency is to try to go to a 1.4 meter propeller. Now, I approached Helix Bjorn at Helix about this, and he came back with a simulation, which is very interesting, uh, of the 1.4 meter versus the 1.3 meter that I have, the actual propeller that I have. And what it shows is that the thrust right here of the 1.3 meter is way down here at 66 kp, and the thrust at the same RPM for the 1.4 meter is up at 90 kp. What that means is that we could maintain level flight at a much lower RPM and therefore lower throttle input, and therefore require less electrical power to maintain level flight. So that is actually quite a big difference, and a very promising result from the simulation. So we'll definitely look to do that in our future tests. So that's all I had for you for this flight, and we'll look to do another soaring flight to test out the different sink rate with the bar out instead of bar neutral, and see how that changes things, maybe improve our flight times, and see the dynamics of the atom wing. So we'll go from there. All right, thanks guys, and we'll see you on the next flight.